In this course, Lance Martin will teach you how to implement RAG from scratch. Lance is a software engineer at LangChain, and LangChain is one of the most common ways to implement RAG. Lance will help you understand how to use RAG to combine custom data with LLMs.
Hi, this is Lance Martin. I'm a software engineer at LangChain. I'm going to be giving a short course focused on RAG, or Retrieval Augmented Generation, which is one of the most popular kind of ideas and applications in LLMs today. So really the motivation for this is that most of the world's data is private, whereas LLMs are trained on publicly available data. So you can kind of see on the bottom on the x-axis the number of tokens used in pre-training various LLMs. So it kind of varies from, say, 1.5 trillion tokens in the case of smaller models like Phi-2, out to some very large number that we actually don't know for proprietary models like GPT-4 or Claude 3. But what's really interesting is that the context window, or the ability to feed external information into these LLMs, is actually getting larger. So about a year ago, context windows were between 4,000 and 8,000 tokens. That's like maybe a dozen pages of text. We've recently seen models all the way out to 1 million tokens, which is thousands of pages of text. So while these LLMs are trained on large-scale public data, it's increasingly feasible to feed them this huge mass of private data that they've never seen. That private data can be your kind of personal data, it can be corporate data, or other information that you want to pass to an LLM that's not natively in its training set. And so this is kind of the main motivation for RAG. It's really the idea that LLMs, one, are kind of the center of a new kind of operating system, and two, it's increasingly critical to be able to feed information from external sources, such as private data, into LLMs for processing. So that's kind of the overarching motivation for RAG. And now RAG refers to Retrieval Augmented Generation, and you can think of it in three very general steps. There's a process of indexing of external data. So you can think about this as, building a database, for example. Many companies already have large-scale databases in different forms. They could be SQL DBs, relational DBs. They could be vector stores, or otherwise. But the point is that documents are indexed such that they can be retrieved based upon some heuristics relative to an input, like a question. And those relevant documents can be passed to an LLM, and the LLM can produce answers that are grounded in that retrieved information. So that's kind of the centerpiece or central idea behind RAG, and why it's really powerful technology, because it's really uniting the knowledge and processing capacity of LLMs with large-scale private external data stores for which most of the important data in the world still lives. And in the following short videos, we're going to kind of build up a complete understanding of the RAG landscape. And we're going to be covering a bunch of interesting papers and techniques that explain kind of how to do RAG. And I've really broken it down into a few different sections. So starting with a question on the left, the first kind of section is what I call query translation. So this captures a bunch of different methods to take a question from a user and modify it in some way to make it better suited for retrieval from one of these indexes we've talked about. That can use methods like query writing. It can be decomposing the query into constituent sub-questions. Then there's a question of routing. So taking that decomposed or rewritten question and routing it to the right place. You might have multiple vector stores, a relational DB, graph DB, and a vector store. So that's the challenge of getting a question to the right source. Then there's kind of the challenge of query construction, which is basically taking natural language and converting it into the DSL necessary for whatever data source you want to work with. A classic example here is text to SQL, which is kind of a very kind of well-studied process, but text to cipher for graph DBs is very interesting. Text to metadata filters for vector DBs is also a very big area of study. Then there's indexing. So that's the process of taking your documents and processing them in some way so that they can be easily retrieved. And there's a bunch of techniques for that we'll talk through. We'll talk through different embedding methods. We'll talk about different indexing strategies. After retrieval, there are different techniques to re-rank or filter retrieved documents. And then finally, we'll talk about generation and kind of an interesting new set of methods to do what we might call as active RAG. So in that retrieval or generation stage, grade documents, grade answers, grade for relevance to the question, grade for faithfulness to the documents, i.e. check for hallucinations, and if either fail, feedback, re-retrieve, or rewrite the question, regenerate the answer, and so forth. So there's a really interesting set of methods we're going to talk through that cover that, like retrieval and generation with feedback. And, in terms of the general outline, we'll cover the basics first. It'll go through indexing, retrieval, and generation, kind of in the bare bones. And then it'll talk through more advanced techniques like we just saw in the prior slide, query transformations, routing, construction, and so forth. Hi, this is Lance from LangChain. This is the second video in our series RAG from Scratch, focused on indexing. So in the past video, you saw the main kind of overall components of RAG pipelines: indexing, retrieval, and generation. And here we're going to kind of deep dive on indexing and give just a quick overview of it. So the first aspect of indexing is we have some external documents that we actually want to load and put into what we're trying to call a retriever. And the goal of this retriever is simply, given an input question, I want to fish out documents that are related to my question in some way. Now, the way to establish that relationship or relevance or similarity is typically done using some kind of numerical representation of documents. And the reason is that it's very easy to compare vectors, for example, with numbers relative to, just free-form text. And so a lot of approaches have been developed over the years to take text documents and compress them down into a numerical representation that then can be very easily searched. Now, there's a few ways to do that. So Google and others came up with many interesting statistical methods where you take a document, you look at the frequency of words, and you build what they call sparse vectors such that the vector locations are, a large vocabulary of possible words. Each value represents the number of occurrences of that particular word. And it's sparse because there's, of course, many zeros. It's a very large vocabulary relative to what's present in the document. And there's very good search methods over this type of numerical representation. Now, a bit more recently, embedding methods that are machine learned. So you take a document and you build a compressed fixed length representation of that document, have been developed with correspondingly very strong search methods over embeddings. So the intuition here is that we take documents and we typically split them because embedding models actually have limited context windows. So, on the order of maybe 512 tokens up to 8,000 tokens or beyond, but they're not infinitely large. So documents are split, and each document is compressed into a vector. And that vector captures the semantic meaning of the document itself. The vectors are indexed. Questions can be embedded in the exactly same way. And then a numerical kind of comparison in some form, using very different types of methods, can be performed on these vectors to fish out relevant documents relative to my question. And let's just do a quick code walkthrough on some of these points. So I have my notebook here. I've installed here. Now I've set a few API keys for Langsmith, which are very useful for tracing, which we'll see shortly. Previously, I walked through this kind of quick start that just showed overall how to lay out these RAG pipelines. And here what I'll do is I'll deep dive a little bit more on indexing, and I'm going to take a question in a document. And first, I'm just going to compute the number of tokens in, for example, the question. And this is interesting because embedding models and LLMs more generally operate on tokens. And so it's kind of nice to understand how large the documents are that I'm trying to feed in. In this case, it's obviously a very small, in this case, question. Now, I'm going to specify OpenAI embeddings. I specify an embedding model here, and I just say embed query. I can pass my question, my document, and what you can see here is that runs, and this is mapped to now a vector of length 1536. And that fixed length vector representation will be computed for both documents, and really for any document. So you're always kind of computing this fixed length vector that encodes the semantics of the text that you've passed. Now I can do things like cosine similarity to compare them. And as we'll see here, I can load some documents. This is just like we saw previously. I can split them, and I can index them here, just like we did before. But we can see under the hood, really what we're doing is we're taking each split, we're embedding it using OpenAI embeddings into this vector representation, and then that's stored with a link to the raw document itself in our vector store. And next we'll see how to actually do retrieval using this vector store. Hi, this is Lance from LangChain, and this is the third video in our series RAG from Scratch, building up a lot of the motivations for RAG from the very basic components. So we're going to be talking about retrieval today. In the last two short videos, I outlined indexing and gave kind of an overview of this flow, which starts with indexing of our documents, retrieval of documents relevant to our question, and then generation of answers based on the retrieved documents. And so we saw that the indexing process basically makes documents easy to retrieve. And it goes through a flow that basically looks like you take our documents, you split them in some way into these smaller chunks that can be easily embedded. Those embeddings are then numerical representations of those documents that are easily searchable, and they're stored in an index. When given a question that's also embedded, the index performs a similarity search and returns splits that are relevant to the question. Now, if we dig a little bit more under the hood, we can think about it like this. If we take a document and embed it, let's imagine that embedding just had 3 dimensions. So, each document is projected into some point in this 3D space. Now, the point is that the location in space is determined by the semantic meaning or content in that document. So to follow that then, documents in similar locations in space contain similar semantic information. And this very simple idea is really the cornerstone for a lot of search and retrieval methods that you'll see with modern vector stores. So in particular, we take our documents, we embed them into this, in this case, a toy 3D space. We take our question, do the same. We can then do a search, like a local neighborhood search you can think about in this 3D space around our question to say, hey, what documents are nearby? And these nearby neighbors are then retrieved because they have similar semantics relative to our question. And that's really what's going on here. So again, we took our documents, we split them, we embed them, and now they exist in this high dimensional space. We've taken our question, embedded it, projected in that same space, and we just do a search around the question for nearby documents and grab ones that are close. And we can pick some number. We can say we want 1 or 2 or 3 or n documents close to my question in this embedding space. And there's a lot of really interesting methods that implement this very effectively. I link one here. And we have a lot of really nice integrations to play with this general idea. So many different embedding models, many different indexes, lots of document loaders, and lots of splitters that can be kind of recombined to test different ways of doing this kind of indexing and retrieval. So now I'll show a bit of a code walkthrough. So here we defined, we kind of had walked through this previously. This is our notebook. We've installed a few packages. We've set a few environment variables using Langsmith. And we showed this previously. This is just an overview showing how to run RAG like kind of end to end. In the last short talk, we went through indexing. And what I'm going to do very simply is I'm just going to reload our documents. So now I have our documents. I'm going to resplit them. And we saw before how we can build our index. Now here, let's actually do the same thing, but in the slides, we actually showed kind of that notion of search in that 3D space. And a nice parameter to think about in building your retriever is K. So K tells you the number of nearby neighbors to fetch when you do that retrieval process. And we talked about, in that 3D space, do I want 1 nearby neighbor or 2 or 3? So here we can specify K equals 1, for example. Now we're building our index, so we're taking every split, embedding it, storing it. Now what's nice is I ask a question, what is task decomposition? This is related to the blog post. And I'm going to run get relevant documents. So I run that. And now how many documents do I get back? I get 1 as expected based upon k equals 1. So this retrieved document should be related to my question. Now I can go to Langsmith and we can open it up and we can look at our retriever and we can see here was our question. Here's the 1 document we got back. And okay, so that makes sense. This document pertains to task decomposition in particular, and it kind of lays out a number of different approaches that can be used to do that. This all kind of makes sense, and this shows kind of in practice how you can implement this kind of KNN or K nearest neighbor search really easily, just using a few lines of code. And next, we're going to talk about generation. Thanks. Hey, this is Lance from LangChain. This is the 4th short video in our RAG from Scratch series that's going to be focused on generation. Now, in the past few videos, we walked through the general flow for kind of basic RAG, starting with indexing, followed by retrieval, then generation of an answer based upon the documents that we retrieved that are relevant to our question. This is kind of the very basic flow. Now, an important consideration in generation is really what's happening is we're taking the documents we retrieve and we're stuffing them into the LLM context window. So if we kind of walk back through the process, we take documents, we split them for convenience or embedding. We then embed each split and we store that in a vector store as this kind of easily searchable numerical representation or vector. And we take a question, embed it to produce a similar kind of numerical representation. We can then search, for example, using something like KNN in this kind of high dimensional space for documents that are similar to our question based on their proximity or location in this space. In this case, you can see 3D as a toy, kind of toy example. Now we've recovered relevant splits to our question. We pack those into the context window and we produce our answer. Now, this introduces the notion of a prompt. So the prompt is kind of you can think of a placeholder that has, for example, in our case, keys. So those keys can be like context and question. So they basically are like buckets that we're going to take those retrieved documents and slot them in. We're going to take our question and also slot it in. And if you kind of walk through this flow, you can kind of see that we can build like a dictionary from our retrieved documents and from our question. And then we can basically populate our prompt template with the values from the dict. And then becomes a prompt value, which can be passed to an LLM, like a chat model, resulting in chat messages, which we then parse into a string and get our answer. So that's like the basic workflow that we're going to see. And let's just walk through that in code very quickly to kind of give you like a hands-on intuition. So we had our notebook we walked through previously, install a few packages. I'm setting a few Langsmith environment variables. We'll see it's nice for kind of observing and debugging our traces. Previously, we did this quick start. We're going to skip that over. And what I will do is I'm going to build our retriever. So again, I'm going to take documents and load them. And then I'm going to split them here. We've kind of done this previously, so I'll go through this kind of quickly. And then we're going to embed them and store them in our index. So now we have this retriever object here. Now I'm going to jump down here. Now here's where it's kind of fun. This is the generation bit. And you can see here I'm defining something new. This is a prompt template. And my prompt template is something really simple. It's just going to say, answer the following question based on this context. It's going to have this context variable and a question. So now I'm building my prompt. So great, now I have this prompt. Let's define an LLM. I'll choose 3.5. Now this introduces the notion of a chain. So in LangChain, we have an expression language called LCEL, LangChain Expression Language, which lets you really easily compose things like prompts, LLMs, parsers, retrievers, and other things. But the very simple kind of example here is just, let's just take our prompt, which you defined right here, and connect it to an LLM, which you defined right here, into this chain. So there's our chain. Now, all we're doing is we're invoking that chain. So every LangChain expression language chain has a few common methods like invoke, batch, stream. In this case, we just invoke it with a dict. So context and question that maps to the expected keys here in our template. And so if we run invoke, what we see is it's just going to execute that chain and we get our answer. Now, if we zoom over to Langsmith, we should see that it's been populated. So yeah, we see a very simple runnable sequence. Here was our document, and here's our output, and here is our prompt. Answer the following question based on the context. Here's the document we passed in. Here is the question, and then we get our answer. So that's pretty nice. Now, there's a lot of other options for RAG prompts. I'll pull one in from our prompt hub. This one's like kind of a popular prompt, so it just like has a little bit more detail, but you know, it's the main intuition is the same. You're passing in documents, you're asking LLM to reason about the documents, given a question, produce an answer. And now here I'm going to define a RAG chain, which will automatically do the retrieval for us. And all I have to do is specify, here's my retriever, which we defined before. Here's our question, which we invoke with. The question gets passed through to the key question in our dict, and it automatically will trigger the retriever, which will return documents, which get passed into our context. So it's exactly what we did up here, except before we did this manually. And now, this is all kind of automated for us. We pass that dict, which is auto-populated, into our prompt, LLM, output parser. Now let's invoke it. And that should all just run. And great, we get an answer, and we can look at the trace, and we can see everything that happened. So we can see our retriever was run. These documents were retrieved. They get passed into our LLM, and we get our final answer. So this is kind of the end of our overview, where we talked about, I'll go back to the slides here quickly. We talked about indexing, retrieval, and now generation. And follow-up short videos will kind of dig into some of the more complex or detailed themes that address some limitations that can arise in this very simple pipeline. Thanks. Hi, this is Lance from LangChain. Over the next few videos, we're going to be talking about query translation. And in this first video, we're going to cover the topic of multi-query. So query translation sits kind of at the first stage of an advanced RAG pipeline. And the goal of query translation is really to take an input user question and to translate it in some way in order to improve retrieval. So the problem statement is pretty intuitive. User queries can be ambiguous. And if the query is poorly written, because we're typically doing some kind of semantic similarity search between the query and our documents, if the query is poorly written or ill-posed, we won't retrieve the proper documents from our index. So there's a few approaches to attack this problem, and you can kind of group them in a few different ways. So here's one way I like to think about it. A few approaches involve query rewriting. So taking a query and reframing it, like writing it from a different perspective. And that's what we're going to talk about a little bit here in depth, using approaches like multi-query or RAG Fusion, which we'll talk about in the next video. You can also do things like take a question and break it down to make it less abstract, like into sub-questions, and there's a bunch of interesting papers focused on that, like Least to Most from Google. You can also take the opposite approach of take a question and make it more abstract. And there's actually an approach we're going to talk about later in a future video called step back prompting that focuses on like kind of a higher level question from the input. So the intuition though for this multi-query approach is we're taking a question and we're going to break it down into a few differently worded questions from different perspectives. And the intuition here is simply that it is possible that the way a question is initially worded, once embedded, it is not well aligned or in close proximity in this high dimensional embedding space to a document that we want to retrieve that's actually related. So the thinking is that by kind of rewriting it in a few different ways, you actually increase the likelihood of actually retrieving the document that you really want to, because of nuances in the way that documents and questions are embedded. This kind of more shotgun approach of taking a question, fanning it out into a few different perspectives may improve and increase the reliability of retrieval. That's like the intuition, really. And of course, we can combine this with retrieval, so we can take our kind of fanned out questions, do retrieval on each one, and combine them in some way and perform RAG. So that's kind of the overview. And now let's go over to our code. So this is a notebook, and we're going to share all this. We're just installing a few packages. We're setting a LangSmith API keys, which we'll see why that's quite useful here shortly. There's our diagram. Now, first, I'm going to index this blog post on agents. I'm going to split it. I'm going to load it. I'm going to split it, and then I'm going to index it in Chroma locally. So this is a vector store. We've done this previously, so now I have my index defined. So here's where I'm defining my prompt for multi-query, which is you're an assistant. Your task is to basically reframe this question into a few different sub-questions. So there's our prompt right here. We'll pass that to an LLM, parse it into a string, and then split the string by new lines. And so we'll get a list of questions out of this chain. That's really all we're doing here. Now, all we're doing is here's a sample input question. There's our generate queries chain, which we defined. We're going to take that list and then simply apply each question to a retriever. So we'll do retrieval per question. And this little function here is just going to take the unique union of documents across all those retrievals. So let's run this and see what happens. So we're going to run this, and we're going to get some set of questions or of documents back. So let's go to LangSmith now. We can actually see what happened under the hood. So here's the key point. We ran our initial chain to generate a set of reframed questions from our input. And here is that prompt. And here is that set of questions that we generated. Now what happened is for every one of those questions, we did an independent retrieval. That's what we're showing here. So that's kind of the first step, which is great. Now I can go back to the notebook and we can show this working end to end. So now we're going to take that retrieval chain, we'll pass it into context of our final RAG prompt. We'll also pass through the question. We'll pass that to our RAG prompt here, pass it to an LLM, and then parse the output. Now let's kind of see how that works. So again, that's okay, there it is. So let's actually go into LangSmith and see what happened under the hood. So this was our final chain. So this is great. We took our input question, we broke it down to these like 5 rephrase questions. For every one of those, we did a retrieval. That's all great. We then took the unique union of documents, and you can see in our final LLM prompt, answer the following question based on the context. This is the final set of unique documents that we retrieved from all of our sub-questions. Here's our initial question. There's our answer. So that kind of shows you how you can set this up really easily, how you can use LangSmith to kind of investigate what's going on, and in particular, use LangSmith to investigate those intermediate questions that you generate in that like kind of question generation phase. And in a future talks, we're going to go through some of these other methods that we kind of introduced at the start of this one. Thank you. This is Lance from LangChain. This is the second video of our deep dive on query translation in our RAG from Scratch series, focused on a method called RAG fusion. So as we kind of showed before, query translation you can think of as the first stage in an advanced RAG pipeline. We're taking an input user question and we're translating it in some way in order to improve retrieval. Now, we showed this general mapping of approaches previously. So again, you have kind of like rewriting. So you can take a question, like kind of break it down into differently worded or different perspectives of the same question. So that's kind of rewriting. There's sub-questions where you take a question and break it down into smaller problems, solve each one independently. And then there's step back where you take a question and kind of go more abstract, where you kind of ask a higher level question as a precondition to answer the user question. So those are the approaches. And we're going to dig into one of the particular approaches for rewriting called RAG fusion. Now, this is really similar to what we just saw with multi-query. The difference being we actually apply a kind of a clever ranking step of our retrieved documents, which we call reciprocal rank fusion. That's really the only difference. The input stage of taking a question, breaking it out into a few kind of differently worded questions, retrieval on each one is all the same. And we're going to see that in the code here shortly. So let's just hop over there and then look at this. So again, here's the notebook that we introduced previously. Here's the packages we've installed. We've set a few API keys for LangSmith, which we'll see why it's quite useful. And you can kind of go down here to our RAG Fusion section. And the first thing you'll note is what our prompt is. So it looks really similar to the prompt we just saw with multi-query. And it's simply your helpful assistant that generates multiple search queries based upon a user input. And here's the question, output 4 queries. So let's define our prompt. And here was our query generation chain. Again, this looks a lot like we just saw. We take our prompt, plumb that into an LLM, and then basically parse by new lines. And that'll basically split out these questions into a list. That's all that's going to happen here. So that's cool. Now here's where the novelty comes in. Each time we do retrieval from one of those questions, we're going to get back a list of documents from our retriever. And so we do it over that. We generate 4 questions here based on our prompt. We do it over 4 questions. Well, like a list of lists, basically. Now, reciprocal rank fusion is really well suited for this exact problem. We want to take this list to list and build a single consolidated list. And really all that's going on is it's looking at the documents in each list and kind of aggregating them into a final output ranking. And that's really the intuition around what's happening here. So let's go ahead and let's go ahead and look at that in some detail. So we can see we run retrieval. That's great. Now let's go over to LangSmith and have a look at what's going on here. So we can see that here is our prompt, your helpful assistant that generates multiple search queries based on a single input. And here is our search queries. And then here are our 4 retrievals. So that's really good. So we know that all is working. And then those retrievals simply went into this rank function and are correspondingly ranked to a final list of 6 unique ranked documents. That's really all we did. So let's actually put that all together into a full RAG chain that's going to run retrieval, return that final list of ranked documents, and pass it to our context, pass through our question, send that to our RAG prompt, pass it to an LM, parse it to an output, and let's run all that together and see that working. Cool. So there's our final answer. Now, let's have a look in LangSmith. We can see here was our 4 questions, here's our retrievals, and then our final RAG prompt plumbed through the final list of ranked 6 questions, which we can see laid out here, and our final answer. So this can be really convenient, particularly if we're operating across like maybe different vector stores, or we want to do like retrieval across a large number of kind of differently worded questions. This reciprocal rank fusion step is really nice. For example, if we wanted to only take the top 3 documents or something, it can be really nice to build that consolidated ranking across all these independent retrievals, then pass that to the LM for the final generation. So that's really the intuition about what's happening here. Thanks. Hi, this is Lance from LangChain. This is our 3rd video focused on query translation in the RAG from Scratch series. And we're going to be talking about decomposition. So query translation in general is a set of approaches that sits kind of towards the front of this overall RAG pipeline. And the objective is to modify or rewrite or otherwise decompose an input question from a user in order to improve retrieval. So we kind of talked through some of these approaches previously, in particular various ways to do query rewriting, like RAG fusion and multi-query. There's a separate set of techniques that have become pretty popular and are really interesting for certain problems, which we might call like kind of breaking down or decomposing an input question into a set of sub-questions. So some of the papers here that are pretty cool
are, for example, this work from Google. And the objective really is first to take an input question and decompose it into a set of subproblems. So this particular example from the paper was the problem of last letter concatenation. And so it took the input question of 3 words, think machine learning, and broke it down into 3 subproblems, think machine learning as the third subproblem. And then you can see in this bottom panel, it solves each one individually. So it shows, for example, in green, solving the problem think machine, where you concatenate the last letter of K with the last letter of machine, or the last letter of think K, last letter of machine E, concatenate those to KE. And then for the overall problem, taking that solution and then and basically building on it to get the overall solution of KEG. So that's kind of one concept of decomposing into subproblems, solving them sequentially. Now, a related work called IRCOT, or interleaved retrieval, combines retrieval with chain of thought reasoning. And so you can kind of put these together into one approach, which you can think of as kind of dynamically retrieval to solve a set of subproblems, kind of that retrieval kind of interleaving with chain of thought, as noted in the second paper, and a set of decomposed questions based on your initial question from the first work from Google. So really the idea here is we're taking one sub-question, we're answering it, we're taking that answer and using it to help answer the second sub-question and so forth. So let's actually just walk through this in code to show how this might work. So this is the notebook we've been working with from some of the other videos. You can see we already have a retriever defined up here at the top. And what we're going to do is we're first going to define a prompt that's basically going to say, given an input question, let's break it down to a set of subproblems or sub-questions which can be solved individually. So we can do that, and this blog post is focused on agents. So let's ask a question about what are the main components of an LLM-powered autonomous agent system. So let's run this and see what the decomposed questions are. So you can see the decomposed questions are, what is LLM technology and how does it work? What are specific components? And then how the components interact. So it's kind of a sane way to kind of break down this problem into a few subproblems which you might attack individually. Now here's where we define a prompt that very simply is going to take our question, we'll take any prior questions we've answered, and we'll take our retrieval and basically just combine them. And we can define this very simple chain. Actually, let's go back and make sure retriever is defined up at the top. So now we are building our retriever. Good, we have that now. So we can go back down here and let's run this. So now we are running, and what's happening is we're trying to solve each of these questions individually using retrieval and using any prior question answers. So, okay, very good. Looks like that's been done. And we can see here's our answer. Now let's go over to LangChain and actually see what happened under the hood. So here's what's kind of interesting and helpful to see. For the first question, so here's our first one. It looks like it just does retrieval, which is what we expect, and then it uses that to answer this initial question. Now for the second question, it should be a little bit more interesting, because if you look at our prompt, here's our question. Now here is our background available question answer pair. So this was the question answer pair from the first question, which we add to our prompt. And then here's the retrieval for this particular question. So we're kind of building up the solution because we're appending the question answer pair from question 1. And then likewise with question 3, it should combine all of that. So we can look at here, here's our question, here's question 1, here's question 2, great. Now here's additional retrieval related to this particular question, and we get our final answer. So that's like a really nice way you can kind of build up solutions using this kind of interleaved retrieval and concatenating prior question answer pairs. I do want to mention very briefly that we can also take a different approach where we can just answer these all individually and then just concatenate all those answers to produce a final answer. And I'll show that really quickly here. It's like a little bit less interesting maybe because you're not using answers from each question to inform the next one. You're just answering them all in parallel. This might be better for cases where it's not really like a sub-question decomposition, but maybe it's like a set of several independent questions whose answers don't depend on each other. That might be relevant for some problems. And we can go ahead and run. Okay, so this ran as well. We can look at our trace. And in this case, yeah, we can see that this actually just kind of concatenates all of our QA pairs to produce the final answer. So this gives you a sense for how you can use query decomposition, employing ideas from 2 different papers that are pretty cool. Thanks. Hi, this is Lance from LangChain. This is the 4th video in our deep dive on query translation in the RAG from Scratch series. And we're going to be focused on step-back prompting. So query translation, as we said in some of the prior videos, kind of sits at the kind of first stage of kind of a RAG pipeline or flow. And the main aim is to take an input question and to translate it or modify it in such a way that it improves retrieval. Now, we talked through a few different ways to approach this problem. So one general approach involves rewriting a question, and we talked about 2 ways to do that: RAG fusion, multi-query. And again, this is really about taking a question and modifying it to capture a few different perspectives, which may improve the retrieval process. Now, another approach is to take a question and kind of make it less abstract, like break it down into sub-questions, and then solve each of those independently. So that's what we saw with like least to most prompting, and a bunch of other variants kind of in that vein of sub-problem solving and then consolidating those solutions into a final answer. Now, a different approach presented by, again, Google as well, is step-back prompting. So step-back prompting kind of takes the opposite approach, where it tries to ask a more abstract question. So the paper talks a lot about using few-shot prompting to produce what they call these step-back or more abstract questions. And the way it does it is it provides a number of examples of step-back questions given your original question. So this is, for example, their per prompt template. You're an expert in world knowledge. I ask you a question. Your response should be comprehensive, not contradict with the following. And this is kind of where you provide your original and then step back. So here's some example questions. So at year saw the creation of the region where the country is located. Which region of the country is the county of Hertfordshire related? Jensen was born in what country? What is Jensen personal history? So that's going to be a more intuitive example. So it's you ask a very specific question about the country someone's born. The more abstract question is just give me the general history of this individual without worrying about that particular more specific question. So let's actually just walk through how this can be done in practice. So again, here's kind of a diagram of the various approaches from less abstraction to more abstraction. Now, here is where we're formulating our prompt using a few of the few-shot examples from the paper. So again, input, something about the police perform lawful arrests and what can members of the police do. So it basically gives the model a few examples. And we basically formulate this into a prompt. That's really all that's going on here. Again, we repeat this overall prompt, which we saw from the paper. You're an expert in world knowledge. Your task is to step back and paraphrase a question, generate a generic step back question, which is easier to answer. Here's some examples. So it's a very intuitive prompt. So, okay, let's start with the question, what is task composition for LLM agents? And we're going to say generate step back question. Okay, so this is pretty intuitive, right? What is the process of task composition? So not worrying as much about agents, but what is a process of task composition in general? And then hopefully that can be independently retrieved. We can independently retrieve documents related to the step back question, and in addition, retrieve documents related to the actual question and combine those to produce kind of final answer. So that's really all that's going on. And here's the response template where we're plumbing in the step back context and our question context. And so what we're going to do here is we're going to take our input question and perform retrieval on that. We're also going to generate our step back question and perform retrieval on that. We're going to plumb those into the prompt as here's our basically our prompt keys, normal question, step back question, and our overall question. Again, we formulate those as a dict. We plumb those into our response prompt, and then we go ahead and attempt to answer our overall question. So we're going to run that. That's running. And okay, we have our answer. Now I want to hop over to Langsmith and attempt to show you kind of what that looked like under the hood. So let's see, let's go into each of these steps. So here was our prompt, right? You're an expert in world knowledge, you're tasked to step back and paraphrase a question. Here were our few shot prompts. And this was our step back question. So what is the process of task composition? Good. From the input, what is task composition for LLM agents? We perform retrieval on both. What is process of task composition? And what is task composition for LLM agents? We perform both retrievals. We then populate our prompt with both. The original question, answer, and then here's the context retrieved from both the question and the step back question. Here's our final answer. So again, this is kind of a nice technique. Probably depends on a lot of the types of the type of domain you want to perform retrieval on. But in some domains where, for example, there's a lot of kind of conceptual knowledge that underpins questions you expect users to ask, this step back approach could be really convenient to automatically formulate a higher level question to, for example, try to improve retrieval. I can imagine if you're working with like kind of textbooks or like technical documentation where you've made independent chapters focused on more high level kind of like concepts, and then other chapters on like more detailed like implementations, this kind of like step back approach and independent retrieval could be really helpful. Thanks. This is Lance from LangChain. This is the 5th video focused on query translation in our RAG from Scratch series. We're going to be talking about a technique called HyDE. So again, query translation sits kind of at the front of the overall RAG flow. And the objective is to take an input question and translate it in some way that improves retrieval. Now, HyDE is an interesting approach that takes advantage of a very simple idea. The basic RAG flow takes a question and embeds it, takes a document and embeds it, and looks for similarity between an embedded document and an embedded question. But questions and documents are very different text objects. So documents can be like very large chunks taken from dense publications or other sources, whereas questions are short, kind of terse, potentially ill-worded from users. And the intuition behind HyDE is take questions and map them into document space using a hypothetical document or by generating a hypothetical document. That's the basic intuition. And the idea kind of shown here visually is that in principle, for certain cases, a hypothetical document is closer to a desired document you actually want to retrieve in this, high dimensional embedding space than the sparse raw input question itself. So again, it's just kind of means of translating raw questions into these hypothetical documents that are then better suited for retrieval. So let's actually do a code walkthrough to see how this works. And it's actually pretty easy to implement, which is really nice. So first, we're just starting with a prompt, and we're using the same notebook that we've used for prior videos. We have a blog post on agents already indexed. So what we're going to do is define a prompt to generate a hypothetical documents. In this case, we'll say write a paper passage to answer a given question. So let's just run this and see what happens. Again, we're taking our prompt, piping it to OpenAI, ChatGPT, and then using string output parser. And so here's a hypothetical document section related to our question. Okay, and this is derived, of course, from the LLM's kind of embedded kind of world knowledge, which is a sane place to generate hypothetical documents.
Now, let's now take that hypothetical document, and basically we're going to pipe that into a retriever. So this means we're going to fetch documents from our index related to this hypothetical document that's been embedded. And you can see we get a few retrieved chunks that are related to this hypothetical document. That's all we've done. And then let's take the final step where we take those retrieved documents here, which we defined, and our question, and we're going to pipe that into this RAG prompt. And then we're going to run our kind of RAG chain right here, which you've seen before, and we get our answer. So that's really it. We can go to Langsmith and we can actually look at what happened. So here, for example, this was our final RAG prompt. Answer the following question based on this context, and here is the retrieved documents that we passed in. So that part's kind of straightforward. We can also look at, okay, this is our retrieval. Okay, no, this is actually what we generated a hypothetical document here. Okay, so this is our hypothetical document. So we've run Chat OpenAI, we've generated this passage, which is our hypothetical document, and then we've run retrieval here. So this is basically showing hypothetical document generation followed by retrieval. So again, here was our passage, which we passed in, and then here's our retrieved documents from the retriever, which are related to the passage content. So again, in this particular index case, it's possible that the input question was sufficient to retrieve these documents. In fact, given prior examples, I know that some of these same documents are indeed retrieved just from the raw question, but in other contexts, that may not be the case. So folks have reported nice performance using HyDE for certain domains. And the really convenient thing is that you can take this document generation prompt, you can tune this arbitrarily for your domain of interest. So it's absolutely worth experimenting with. It's a neat approach that can overcome some of the challenges with retrieval. Thanks very much. Hi, this is Lance from LangChain. This is the 10th video in our RAG from Scratch series focused on routing. So we talked through query translation, which is the process of taking a question and translating it in some way. It could be decomposing it, using step-back prompting, or otherwise. But the idea here was take our question, change it into a form that's better suited for retrieval. Now, routing is the next step, which is basically routing that potentially decomposed question to the right source. And in many cases, that could be a different database. So let's say in this toy example, we have a vector store, a relational DB, and a graph DB. What we do with routing is we simply route the question based upon the content of the question to the relevant data source. So there's a few different ways to do that. One is what we call logical routing. In this case, we basically give an LLM knowledge of the various data sources that we have at our disposal, and we let the LLM kind of reason about which one to apply the question to. So it's kind of like the LLM is applying some logic to determine which data source, for example, to use. Alternatively, you can use semantic routing, which is where we take a question, we embed it, and for example, we embed prompts. We then compute the similarity between our question and those prompts, and then we choose a prompt based upon the similarity. So the general idea is, in our diagram, we talk about routing to, for example, a different database, but it can be very general. It can be routing to a different prompt. It can be really arbitrarily taking this question and sending it to different places, be it different prompts, be it different vector stores. So let's walk through the code a little bit. So you can see, just like before, we've done a few pip installs, we've set up Langsmith, and let's talk through logical routing first. So in this toy example, let's say we had, for example, 3 different docs. Like we had Python docs, we had JS docs, we had Golang docs. What we want to do is take a question, route it to one of those 3. So what we're actually doing is we're setting up a data model, which is basically going to be bound to our LLM and allow the LLM to output one of these 3 options as a structured object. So you can really think of this as like classification. Classification plus function calling to produce a structured output, which is constrained to these 3 possibilities. So the way we do that is, let's just zoom in here a little bit. We can define like a structured object that we want to get out from our LLM. Like in this case, we want, for example,
one of these three data sources to be output, we can take this and we can actually convert it into OpenAI, for example, function schema. And then we actually pass that in and bind it to our LLM. So what happens is we ask a question, our LLM invokes this function on the output to produce an output that adheres to the schema that we specify. So in this case, for example, we output in this toy example, let's say we wanted an output to be data source, vector store, or SQL database. The output will contain a data source object, and it'll be one of the options we specify as a JSON string. We also instantiate a parser from this object to parse that JSON string to an output like a pedantic object, for example. So that's just one toy example. And let's show one up here. So in this case, again, we had our three doc sources. We bind that to our LLM. So you can see we do with structured output. Basically, under the hood, that's taking that object definition, turning it into function schema, and binding that function schema to our LLM. And we call our prompt, you're an expert at routing a user question based on programming language that user is referring to. So let's define our router here. Now what we're going to do is we'll ask a question that is Python code. So we'll call that, and now it's done. And you can see the object we get out is indeed, it's a route query object. So it adheres to this data model we've set up. And in this case, it's correct. So it's calling this Python doc. So we can extract that right here as a string. Now, once we have this, you can really easily set up like a route. So this could be like our full chain where we take this router we should define here, and then this choose route function can basically take that output and do something with it. So for example, if Python docs, this could then apply the question to like a retriever full of Python information, or JS, same thing. So this is where you would hook basically that question up to different chains that are like, retriever chain 1 for Python, retriever chain 2 for JS, and so forth. So this is kind of like the routing mechanism, but this is really doing the heavy lifting of taking an input question and turning it into a structured object that restricts the output to one of a few output types that we care about in our like routing problem. So that's really kind of the way this all hooks together. Now, semantic routing is actually maybe a little bit more straightforward based on what we've seen previously. So in that case, let's say we have two prompts. We have a physics prompt, we have a math prompt. We can embed those prompts, no problem, we do that here. Now, let's say we have an input question from a user, like in this case, what is a black hole? We pass that through. We then apply this runnable lambda function, which is defined right here. What we're doing here is we're embedding the question. We're computing similarity between the question and the prompts. We're taking the most similar, and then we're basically choosing the prompt based on that similarity. And you can see, let's run that and try it out. And we're using the physics prompt, and there we go, black holes, region, and space. So that just shows you kind of how you can use semantic routing to basically embed a question, embed, for example, various prompts, pick the prompt based on semantic similarity. So that really gives you just two ways to do routing. One is logical routing with function calling. It can be used very generally. In this case, we applied it to like different coding languages, but imagine these could be swapped out for like, my Python, my like vector store versus my GraphDB versus my relational DB. And you could just very simply have some description of what each is. And, then not only will the LLM do reasoning, but it'll also return an object that can be parsed very cleanly to produce like one of a few very specific types, which then you can reason over like we did here in your routing function. So that kind of gives you the general idea, and these are really, very useful tools, and I encourage you to experiment with them. Thanks. Hi, this is Lance from LangChain. This is the 11th part of our RAG from Scratch video series focused on query construction. So we previously talked through query translation, which is the process of taking a question and converting it or translating it into a question that's better optimized for retrieval. Then we talked about routing, which is the process of taking that question and routing it to the right source, be it a given vector store, GraphDB, or SQLDB, for example. Now we're going to talk about the process of query construction, which is basically taking natural language and converting it into particular domain-specific language for one of these sources. Now, we're going to talk specifically about the process of going from natural language to metadata filters for vector stores. The problem statement is basically this. Let's imagine we had an index of LangChain video transcripts. You might want to ask a question. Give me, or find me videos on Chat LangChain published after 2024, for example. The process of query structuring basically converts this natural language question into a structured query that can be applied to the metadata filters on your vector store. So most vector stores will have some kind of metadata filters that can do kind of structured querying on top of the chunks that are indexed. So for example, this type of query will retrieve all chunks that talk about the topic of Chat LangChain published after the date 2024. That's kind of the problem statement. And to do this, we're going to use function calling. In this case, you can use, for example, OpenAI or other providers to do that. And what we're going to do is, at a high level, take the metadata fields that are present in our vector store and provide them to the model as kind of information. And the model then can take those and produce queries that adhere to the schema provided. And then we can parse those out to a structured object like a pydantic object, which can then be used in search. So that's kind of the problem statement. And let's actually walk through code. So here's our notebook, which we've kind of gone through previously. And I'll just show you as an example. Let's take an example YouTube video and let's look at the metadata that you get with the transcript. So you can see you get stuff like description, URL, publish date, length, things like that. Now let's say we had an index that had basically a number of different metadata fields and filters that allowed us to do range filtering on like view count, publication date, the video length, or unstructured search on contents and title. So those are kind of like imagine we had an index that had those kind of filters available to us. What we can do is capture that information about the available filters in an object. So we're calling that this tutorial search object kind of encapsulates that information about the available searches that we can do. And so we basically enumerated here, content search and title search are semantic searches that can be done over those fields. And then these filters then are various types of structured searches we can do on like the length, the view count, and so forth. And so we can just kind of build that object. Now we can set this up really easily with a basic simple prompt that says, you're an expert, can bring natural language into database queries. You have access to the database tutorial videos. Given a question, return a database query optimized for retrieval. So that's kind of it. Now here's the key point though. When you call this LLM with structured output, you're binding this pydantic object, which contains all the information about our index, to the LLM, which is exactly what we talked about previously. It's really this process right here. You're taking this object, you're converting it into a function schema, for example, OpenAI, you're binding that to your model, and then you're going to be able to get a structured object out versus a JSON string from a natural language question, which can then be parsed into a pydantic object, which you get out. So that's really the flow. And it's taking advantage of function calling, as we said. So if we go back down, we set up our query analyzer chain right here. Now let's try to run that just on a purely semantic input. So RAG from scratch, let's run that. And you can see this just does like a content search and a title search. That's exactly what we would expect. Now if we pass a question that includes like a date filter, let's just see if that would work. And there we go. So you kind of still get that semantic search, but you also get search over, for example, published date, earliest and latest published date, kind of as you would expect. Let's try another one here. So videos focus on the topic of Chat LangChain. They're published before 2024. This is just kind of a rewrite of this question in a slightly different way using a different date filter. And again, you can see we get content search, title search, and then we can get kind of a date search. So this is a very general strategy that can be applied kind of broadly to different kinds of querying you want to do. It's really the process of going from an unstructured input to a structured query object out, following an arbitrary schema that you provide. And so as noted, really this whole thing we created here, this tutorial search, is based upon the specifics of our vector store of interest. And if you want to learn more about this, I linked to some documentation here. that talks a lot about different types of integrations we have with different vector store providers to do exactly this. So it's a very useful trick. It allows you to do kind of query, say metadata filtering on the fly from a natural language question. It's a very convenient trick that works with many different vector DBs. So encourage you to play with it. Thanks. This is Lance from LangChain. I'm going to talk about indexing and multi-representation indexing in particular for the 12th part of our RAG from Scratch series here. So we previously talked about a few different major areas. We talked about query translation, which takes a question and translates it in some way to optimize for retrieval. We talked about routing, which is the process of taking a question, routing it to the right data source, be it a vector store, GraphDB, SQLDB. We talked about query construction. We dug into basically query construction for vector stores, but of course there's also text to SQL, text to cipher. So now we're going to talk about indexing a bit. In particular, we're going to talk about indexing techniques for vector stores. And I want to highlight one particular method today called multi-representation indexing. So the high-level idea here is derived a bit from a paper called proposition indexing, which kind of makes a simple observation. You can think about decoupling raw documents and the units you use for retrieval. So in the typical case, you take a document, you split it up in some way to index it, and then you embed the split directly. This paper talks about actually taking a document, splitting it in some way, but then using an LLM to produce what they call a proposition, which you can think of as like kind of a distillation of that split. So it's kind of like using an LLM to modify that split in some way to distill it or make it like a crisper, like summary, so to speak, that's better optimized for retrieval. So that's kind of one piece of intuition. So we've actually taken that idea and we've kind of built on it a bit in kind of a really nice way that I think is very well suited actually for long context LLMs. So the idea is pretty simple. You take a document and you actually distill it or create a proposition like they showed in the prior paper. I kind of typically think of this as just produce a summary of the document and you embed that summary. So that summary is meant to be optimized for retrieval. So it might contain a bunch of keywords from the document or like the big ideas, such that when you embed the summary, you embed a question, you do search, you basically can find that document based upon this highly optimized summary for retrieval. So that's kind of represented here in your vector store. But here's the catch. You independently store the raw document in a doc store. And when you basically retrieve the summary in the vector store, you return the full document for the LLM to perform generation. And this is a nice trick because at generation time, now with long context LLMs, for example, the LLM can handle that entire document. You don't need to worry about splitting it or anything. You just simply use the summary to create a really nice representation for fishing out that full doc. Use that full doc in generation. There might be a lot of reasons you want to do that. You want to make sure the LLM has the full context to actually answer the question. So that's the big idea. It's a nice trick. And let's walk through some code here. So we have a notebook all set up. Just like before, we've done some pip installs, set some API keys here for Langsmith. Kind of here's a diagram. Now let me show an example. Let's just load two different blog posts. One is about agents. One is about human data quality. And what we're going to do is let's create a summary of each of those. So this is kind of the first step of that process where we're going from like the raw documents to summaries. Let's just have a look and make sure those ran. So, okay, cool. So the first doc discusses, building autonomous agents. The second doc contains the importance of high quality human data and training. Okay, so that's pretty nice. We have our summaries. Now we're going to go through a process that's pretty simple. First, we define a vector store that's going to index those summaries. Then we're going to define what we call like our document store, which is going to store the full documents. Okay, so this multi-vector retriever kind of just pulls those two things together. We basically add our doc store. We add this byte store is basically the full document store. The vector store is our vector store. And now this ID is what we're going to use to reference between the chunks or the summaries and the full documents. That's really it. So now for every document, we'll define a new doc ID. And then we're basically going to like take our summary documents and we're going to extract for each of our summaries, we're going to get the associated doc ID. So there we go. So let's go ahead and do that. So we have our summary docs, which we add to the vector store. We have our full documents, our doc IDs, and the full raw documents, which are added to our doc store. And then let's just do a query at vector store, like a similarity search on our vector store. So memory and agents, and we can see, okay, so we can extract, from the summaries, we can get, for example, the summary that pertains to agents. So that's a good thing. Now let's go ahead and run a query, get relevant documents on our retriever, which basically combines the summaries, which we use for retrieval, then the doc store, which we use to get the full doc back. So we're going to apply our query. We're going to basically run this. And here's the key point. We've gotten back the entire article. And we can actually, if you want to look at the whole thing, we can just go ahead and do this. Here we go. So this is the entire article that we get back from that search. So it's a pretty nice trick. Again, we queried with just memory and agents. And we can kind of go back to our diagram here. We queried for memory and agents. It searched our summaries. It found the summary related to memory and agents. It uses that doc ID to reference between the vector store and the doc store. It fishes out the right full doc, returns us the full document, in this case, the full web page. That's really it. Simple idea, nice way to go from basically like nice, simple proposition style or summary style indexing to full document retrieval, which is very useful, especially with long context LLMs. Thank you. Hi, this is Lance from LangChain. This is the 13th part of our RAG from Scratch series, focused on a technique called RAPTOR. So RAPTOR sits within kind of an array of different indexing techniques that can be applied on vector stores. We just talked about multi-representation indexing. I provided a link to a video that's very good, talking about the different means of chunking, so I encourage you to look at that. And we're going to talk today about a technique called RAPTOR, which you can kind of think about as a technique for hierarchical indexing. So the high-level intuition is this. Some questions require very detailed information from a corpus to answer, like pertain to a single document or single chunk. So like we can call those low-level questions. Some questions require consolidation across kind of broad swaths of a document. So across like many documents or many chunks within a document. And you can call those like higher level questions. And so there's kind of this challenge in retrieval in that typically when you do like k nearest neighbors retrieval, like we've been talking about, you're fishing out some number of chunks. But what if you have a question that requires information across like 5, 6, or a number of different chunks, which may exceed, the k parameter in your retrieval. So again, when you typically do retrieval, you might set a k parameter of 3, which means you're retrieving 3 chunks from your vector store. And maybe you have a very high level question that could benefit from information across more than 3. So this technique called RAPTOR is basically a way to build a hierarchical index of document summaries. And the intuition is this. You start with a set of documents as your leaves here on the left. You cluster them, and then you summarize each cluster. So each cluster of similar documents will consolidate information from across your context, which is, your context could be a bunch of different splits, or it could even be across a bunch of different documents. You're basically capturing similar ones, and you're consolidating the information across them in a summary. And here's the interesting thing. You do that recursively until either you hit like a limit or you end up with one single cluster that's a kind of very high level summary of all of your documents. And what the paper shows is that if you basically just collapse all these and index them together as a big pool, you end up with a really nice array of chunks that span the abstraction hierarchy. Like you have a bunch of chunks from individual documents that are just like more detailed chunks pertaining to that, single document. But you also have chunks from these summaries, or I would say like, maybe not chunks, but in this case, the summary is like a distillation. So, raw chunks on the left that represent your leaves are kind of like the rawest form of information, either raw chunks or raw documents. and then you have these higher level summaries, which are all indexed together. So if you have higher level questions, they should basically be more similar in semantic search, for example, to these higher level summary chunks. If you have lower level questions, then they'll retrieve these more lower level chunks. And so you have better semantic coverage across like the abstraction hierarchy of question types. That's the intuition. They do a bunch of nice studies to show that this works pretty well. I actually did a deep dive video just on this, which I link below. I did want to cover it briefly, just at a very high level. So let's actually just do kind of a code walkthrough. And I've added it to this RAG from Scratch course notebook, but I link over to my deep dive video as well as the paper and the full code notebook, which is already checked in and is discussed at more length in the deep dive. The technique is a little bit detailed, so I only want to give you very high levels kind of overview here, and you can look at the deep dive video if you want to go in more depth. Again, we talked through this abstraction hierarchy. I applied this to a large set of LangChain documents. So this is me loading basically all of our LangChain expression language docs. So this is on the order of 30 documents. You can see I do a histogram here of the token counts per document. Some are pretty big, most are fairly small, less than 4,000 tokens. And what I did is I indexed all of them individually. So all those raw documents you can kind of imagine are here on the left. And then I do embedding, I do clustering, summarization, and I do that recursively until I end up with, in this case, I believe I only set like 3 levels of recursion, and then I save them all in my vector store. So that's like the high level idea. I'm applying this RAPTOR technique to a whole bunch of LangChain documents that have fairly large number of tokens. So I do that. And yeah, I use both Claude as well as OpenAI here. This talks through the clustering method that they use, which is pretty interesting. You can kind of dig into that on your own if you're really interested. This is a lot of their code, which I cite accordingly. This is basically implementing the clustering method that they use. And this is just simply the document embedding stage. This is like basically embedding and clustering. That's really it. Some text formatting, summarizing of the clusters right here. And then this is just running that whole process recursively. That's really it. This is tree building. So basically, I have the raw docs. Let's just go back and look at doc texts. So this should be all my raw documents. So that's right, you can see it here. Doc text is basically just the text in all those LangChain documents that I pulled. And so I run this process on them right here. So this is that recursive embedding cluster, basically runs and produces that tree. Here's the results. This is me just going through the results and basically adding the result text to this list of texts. Okay, so here's what I do. This leaf text is all the raw documents, and I'm appending to that all the summaries. That's all that's going on. And then I'm indexing them all together. That's the key point. RAG chain, and there you have it. That's really all you do. So anyway, I encourage you to look at this in depth. It's a pretty interesting technique. It works well with long contexts. So for example, one of the arguments I made is that it's kind of a nice approach to consolidate information across like a span of large documents. Like in this particular case, my individual documents were LangChain expression language docs, each being somewhere on the order of, in this case, like, most of them are less than 4,000 tokens, some pretty big, but I index them all. I cluster them without any splits, embed them, cluster them, build this tree, and go from there. And it all works because we now have LLMs that can go out to, 100 or 200,000 up to 1 million tokens in context. So you can actually just do this process for big swaths of documents in place without any splitting. It's a pretty nice approach. So I encourage you to think about it, look at it, watch the deep dive video if you really want to go deeper on this. Thanks. Hi, this is Lance from LangChain. This is the 14th part of our RAG from Scratch series. I'm going to be talking about an approach called ColBERT. So we've talked about a few different approaches for indexing. And just as kind of a refresher, indexing falls kind of right down here in our flow. We started initially with query translation, taking a question, translating it in some way to optimize retrieval. We talked about routing it to a particular database. We then talked about query construction, so going from natural language to the DSL or domain-specific language for any of the databases that you want to work with. So those are, metadata filters for vector stores, or Cypher for GraphDB, or SQL for relational DB. So that's kind of the flow we talked about today. We talked about some indexing approaches like multi-representation indexing. We gave a small shout out to Greg Cameron and his series on chunking. We talked about hierarchical indexing. And I wanted to include one advanced kind of embedding approach. So we talked a lot about embeddings are obviously very central to semantic similarity search and retrieval. So one of the interesting points that's been brought up is that embedding models, of course, take a document, you can see here on the top, and embed it, basically compress it to a vector. So it's kind of a compression process. You're representing all the semantics of that document in a single vector. You're doing the same to your question. You're doing a similarity search between the question embedding and the document embedding in order to perform retrieval. You're typically taking the k most similar document embedding is given a question, and that's really how you're doing it. Now, a lot of people have said, well, hey, compressing a full document with all this nuance to a single vector seems like a little bit overly restrictive, right? And this is a fair question to ask. There's been some interesting approaches to try to address that. And one is this approach method called ColBERT. So the intuition is actually pretty straightforward. There's a bunch of good articles I linked down here. This is my little cartoon to explain it, which I think is hopefully kind of helpful. But here's the main idea. Instead of just taking a document and compressing it down to a single vector, basically a single, what we might call an embedding vector, we take the document, we break it up into tokens. So tokens are just like, units of content. It depends on the tokenizer you use. We talked about this earlier. So you basically tokenize it. And you produce basically an embedding or a vector for every token. And there's some kind of positional weighting that occurs when you do this process. So obviously you look at the implementation to understand the details, but the intuition is that you're producing some kind of representation for every token, okay? And you're doing the same thing for your questions. So you're taking your question, you're breaking it into tokens, and you have some representation or vector per token. And then what you're doing is, for every token in the question, you're computing the similarity across all the tokens in the document. And you're finding the max. So you're taking the max, you're storing that, and you're doing that process for all the tokens in the question. So again, token 2, you compare it to every token in the document, compute the max. And then the final score is, in this case, the sum of the max similarities between every question token and any document token. So it's an interesting approach. It reports very strong performance. Latency is definitely a question. So kind of production readiness is something you should look into. But it's an approach that's worth mentioning here because it's pretty interesting. And let's walk through the code. So there's actually a really nice library called Ratatouille, which makes it very easy to play with ColBERT. So just pip install it here. I've already done that. And we can use one of their pre-trained models to mediate this process. So I'm basically following their documentation. This is kind of what they recommended. So I'm running this now. Hopefully this runs somewhat quickly. I'm not sure. I previously have loaded this model, so hopefully it won't take too long. And yeah, you can see it's pretty quick. I'm on a Mac M2 with 32 gigs. So just as like a context in terms of my system. This is from their documentation. We're just grabbing a Wikipedia page. This is getting a full document on Miyazaki. So that's cool. We're going to grab that. Now, this is just from their docs. This is basically how we create an index. So we provide the, some index name, the collection, the max document length, and yeah, you should look at their documentation for these flags. These are just the defaults. So I'm going to create my index. So I get some logging here, so it's working under the hood. And by the way, I actually have their documentation open, so you can kind of follow along. Let's see, yeah, right about here. So you can kind of follow this indexing process to create an index. So you need to load a trained model. This can be either your own pre-trained model or one of ours from the hub. And this is kind of the process we're doing right now. Create index is just a few lines of code, and this is exactly what we're doing. So this is the, my documents, and this is the indexing step that we just kind of walked through, and it looks like it's done. So you get a bunch of logging here. That's fine. Now let's actually see if this works. So we're going to run RAG search. What in Motion Studio did Miyazaki found? Set our K parameter, and we get some results. Okay, so it's running, and cool, we get some documents out. So, it seems to work. Now, what's nice is you can run this within LangChain as a LangChain retriever. So that basically wraps this as a LangChain retriever, and then you can use it freely as a retriever within LangChain. It works with all the other different LLMs and all their components like re-rankers and so forth that we talked through. So you can use this directly as a retriever. Let's try this out, and boom, nice and fast. And we get our documents. Again, this is a super simple test example. You should run this maybe on more complex cases, but it's pretty easy to spin up. It's a really interesting alternative indexing approach, using, again, like we talked through, a very different algorithm for computing doc similarity that may work better. I think an interesting regime to consider this would be longer documents. So if you want like longer, if you basically want kind of long context embedding, I think you should look into, for example, the max token limits for this approach, because it partitions the document into each token. I would be curious to dig into kind of what the overall context limits are for this approach of ColBERT, but it's really interesting to consider, and it reports very strong performance. So again, I encourage you to play with it, and this is just kind of an intro to how to get set up and to start experimenting with it really quickly. Thanks. This is Lance from LangChain. I'm going to be talking about using LangGraph to build diverse and sophisticated RAG flows. So just to set the stage, the basic RAG flow you can see here starts with a question, retrieval of relevant documents from an index, which are passed into the context window of an LLM for generation of an answer grounded in the retrieved documents. So that's kind of the basic outline. And we can see it's like a very linear path. In practice, though, you often encounter a few different types of questions, like when do we actually want to retrieve, based upon the context of the question. Are the retrieved documents actually good or not? And if they're not good, should we discard them? And then how do we loop back and retry retrieval with, for example, an improved question? So these types of questions motivate an idea of active RAG, which is a process where an LLM actually decides when and where to retrieve based upon like existing retrievals or existing generations. Now, when you think about this, there's a few different levels of control that you have over an LLM in a RAG application. The base case, like we saw with our chain, is you just use an LLM to choose a single steps output. So for example, in traditional RAG, you feed it documents and it decides the generation. So it's just kind of one step. Now, a lot of RAG workflows will use the idea of routing. So like given a question, should I route it to a vector store or a GraphDB? And we have seen this quite a bit. Now, this newer idea that I want to introduce is how do we build more sophisticated logical flows in a RAG pipeline that you let the LLM choose between different steps, but specify all the transitions that are available. And this is known as we call a state machine. Now, there's a few different architectures that have emerged to build different types of RAG chains. And of course, chains are traditionally used just for like very basic RAG. But this notion of a state machine is a bit newer. And LangGraph, which we recently released, provides a really nice way to build state machines for RAG and for other things. And the general idea here is that you can lay out more diverse and complicated RAG flows and then implement them as graphs. And it kind of motivates this more broad idea of like flow engineering and thinking through the actual like workflow that you want and then implementing it. And we're going to actually do that right now. So I'm going to pick a recent paper called CRAG, corrective RAG, which is really a nice method for active RAG that incorporates a few different ideas. So first you retrieve documents, and then you grade them. Now, if at least one document exceeds the threshold for relevance, you go to generation. You generate your answer. And it does this knowledge refinement stage after that, but let's not worry about that for right now. It's kind of not essential for understanding the basic flow here. So again, you do a grade for relevance for every document. If any is relevant, you generate. Now, if they're all ambiguous or incorrect based upon your grader, you retrieve from an external source. They use web search. And then they pass that as their context for answer generation. So it's a really neat workflow where you're doing retrieval just like with basic RAG, but then you're reasoning about the documents. If they're relevant, go ahead and at least one is relevant, go ahead and generate. If they're not, retrieve from an alternative source and then pack that into the context and generate your answer. So let's see how we would implement this as a state machine using LangGraph. We'll make a few simplifications. We're going to first decide if any documents are relevant. We'll go ahead and do the web search to supplement the output. So that's just like kind of one minor modification. We'll use tabulated search for web search. We'll use query writing to optimize the search to optimize the web search, but it follows a lot of the intuitions of the main paper. Small note here, we set the tabulate API key. And another small note, I've already set my Langsmith API key, which we'll see is useful a bit later for observing the resulting traces. Now, I'm going to index 3 blog posts that I like. I'm going to use ChromaDB. I'm going to use OpenAI embeddings. I'm going to run this right now. So this will create a vector store for me from these 3 blog posts. And then what I'm going to do is define a state. Now, this is kind of the core object that's going to be passed around my graph that I'm going to modify. And right here is where I define it. And the key point to note right now is it's just a dictionary. And it's going to contain things that are relevant for RAG, like question, documents, generation. And we'll see how we update that in a little bit. But the first thing to note is we define our state, and this is what's going to be modified in every node of our graph. Now, here's really the crux of it. And this is the thing I want to zoom in on a little bit. So when you kind of move from just thinking about prompts to thinking about overall flows, it's like kind of a fun and interesting exercise. I kind of think about this as, it's been mentioned on Twitter a little bit, more like flow engineering. So let's think through what was actually done in the paper and what modifications to our state are going to happen in each stage. So we start with a question. You can see that on the far left. And this kind of state is represented as a dictionary like we have. We start with a question. We perform retrieval from our vector store, which we just created. That's going to give us documents. So that's one node. We made an adjustment to our state by adding documents. That's step one. Now we have a second node where we're going to grade the documents. And in this node, we might filter some out. So we are making a modification to state, which is why it's a node. So we're going to have a grader. Then we're going to have what we're going to call a conditional edge. So we saw we went from question to retrieval. Retrieval always goes to grading. And now we have a decision. If any document is irrelevant, we're going to go ahead and do web search to supplement. And if they're all relevant, we'll go to generation. It's a minor kind of logical decision that we're going to make. If any are not relevant, we'll transform the query and we'll do web search and we'll use that for generation. So that's really it. And that's how we can kind of think about our flow and how our states can be modified throughout this flow. Now, all we then need to do, and I kind of found spending 10 minutes thinking carefully through your flow engineering is really valuable, because from here, it's really just implementation details. And it's pretty easy, as you'll see. So basically, I'm going to run this code block, but then we can like walk through some of it. I won't show you everything, so it'll get a little bit boring. But really, all we're doing is we're finding functions for every node that take in the state and modify it in some way. That's all that's going on. So think about retrieval. We run retrieval, we take in state. Remember, it's a dict. We get our state dict like this. We extract one key question from our dict. We pass that to a retriever, we get documents, and we write back out state, now with documents key added. That's all. Generate's going to be similar. We take in state. Now we have our question and documents. We pull in a prompt. We define an LLM. We do minor post-processing on documents. We set up a chain for retrieval, for generation, which is just going to be take our prompt, plumb that to an LLM, parse the output to a string, and we run it right here, invoking our documents and our question to get our answer. We write that back to state. That's it. And you can kind of follow here, for every node, we just define a function that performs the state modification that we want to do on that node. Grading documents is going to be the same. In this case, I do a little thing extra here because I actually define a Pydantic data model for my grader, so that the output of that particular grading chain is a binary yes or no. You can look at the code. I'll make sure it's all shared. And that just makes sure that our output is very deterministic, so that we then can down here perform logical filtering. So what you can see here is we define this search value, no, and we iterate through our documents. We grade them. If any document is graded as not relevant, we flag this search thing to yes. That means we're going to perform web search. We then add that to our state dict at the end. So run web search. Now that value is true. That's it. And you can kind of see we go through some other nodes here. There's a web search node. Now here is where our one conditional edge we define right here. This is where we decide to generate or not, based on that search key. So we, again, get our state. Let's extract the various values. So we have this search value now. If search is yes, we return the next node that we want to go to. So in this case, it'll be transform query, which will then go to web search. Else, we go to generate. So what we can see is we laid out our graph, which you can kind of see up here. And now we define functions for all those nodes, as well as the conditional edge. And now we scroll down. All we have to do is just lay that out here, again, as our flow. And this is kind of what you might think of as like kind of flow engineering, where you're just laying out the graph as you drew it, where we have set our entry point as retrieve. We're adding an edge between retrieve and grade documents. So we went retrieval, grade documents, we add our conditional edge. Depending on the grade, either transform the query, go to web search, or just go to generate. We create an edge between transform the query and web search, then web search to generate, and then we also have an edge generate to end. And that's our whole graph. That's it. So we can just run this. And now I'm going to ask a question. So let's just say, how does agent memory work, for example? Let's just try that. And what this is going to do is going to print out what's going on as we run through this graph. So first we can see output from retrieve. This is going to be all of our documents that we retrieved. So that's fine. This is from our retriever. Then you can see that we're doing a relevance check across our documents. And this is kind of interesting, right? You can see we're grading them here. One is graded as not relevant. And okay, you can see the documents are now filtered because we removed the one that's not relevant. And because one is not relevant, we decide, okay, we're going to just transform the query and run web search. And you can see after query transformation, we rewrite the question slightly. We then run web search. And you can see from web search, it searched from some additional sources, which you can actually see here. It's appended as so here it is. So here it's a new document appended from web search, which is from memory knowledge requirements. So it basically looked up some AI architecture related to memory web results. So that's fine. That's exactly what we want to do. And then we generate a response. So that's great. And this is just showing you everything in kind of gory detail. But I'm going to show you one other thing that's really nice about this. If I go to LangSmith, I have my API key set, so all my generations are just logged to LangSmith. And I can see my LangGraph run here. Now what's really cool is this shows me all of my nodes. So remember, we had retrieve, grade, we evaluated the grade. Because one was irrelevant, we then went ahead and transformed the query. We did a web search. We appended that to our context. You can see all those steps are laid out here. In fact, you can even look at every single grader and its output. I will move this up slightly. So you can see the different scores for grades. Okay, so this particular retrieval was graded as not relevant. So that's fine. That can happen in some cases. And because of that, we did a query transformation. So we modified the question slightly. How does the memory system and artificial agents function? So it's just a minor rephrasing of the question. We did this Tavily web search. This is where it queried from this particular blog post from Medium. So it's like a sane web query. We can like sanity check it. And then what's neat is we can go to our generate step, look at OpenAI, and here's our full prompt. How does the memory system and artificial agents function? And then here's all of our documents. So this is the web search, as well as we still have the relevant chunks that were retrieved from our blog posts. And then here's our answer. So that's really it. You can see how really moving from the notion of just like, I'll actually go back to the original. Moving from, I will try to open this up a little bit. Yeah, I can see my face still. The transition from laying out simple chains to flows is a really interesting and helpful way of thinking about why graphs are really interesting, because you can encode more sophisticated logical reasoning workflows, but in a very like clean and well-engineered way where you can specify all the transitions that you actually want to have executed. And I actually find this way of thinking and building kind of logical like workflows really intuitive. We have a blog post coming out tomorrow that discusses both implementing self-RAG as well as CRAG for two different active RAG approaches using this idea of state machines and LangGraph. So I encourage you to play with it. I found it really intuitive to work with. I also found inspection of traces to be quite intuitive using LangGraph, because every node is enumerated pretty clearly for you, which is not always the case when you're using other types of more complex reasoning approaches, for example, like agents. So in any case, I hope this was helpful. And I definitely encourage you to check out kind of this notion of like flow engineering using LangGraph. And in the context of RAG, it can be really powerful, hopefully, as you've seen here. Thank you.
Hey, this is Lance from LangChain. I want to talk to a recent paper that I saw called Adaptive RAG, which brings together some interesting ideas that have kind of been covered in other videos, but this actually ties them all together in kind of a fun way. So the two big ideas to talk about here are one of query analysis. So we've actually done kind of a whole RAG from scratch series that walks through each of these things in detail, but this is a very nice example of how this comes together with some other ideas we've been talking about. So query analysis is typically the process of taking an input question and modifying it in some way to better optimize retrieval. There's a bunch of different methods for this. It could be decomposing it into sub-questions. It could be using some clever techniques like step-back prompting. But that's kind of like the first stage of query analysis. Then typically you can do routing. So you route a question to one of multiple potential sources. It could be one or two different vector stores. It could be a relational DB versus a vector store. It could be web search. It could just be like an LLM fallback, right? So this is like one kind of big idea, query analysis, right? It's kind of like the front end of your RAG pipeline. It's taking your question, it's modifying it in some way, it's sending it to the right place, be it a web search, be it a vector store, be it a relational DB. So that's kind of topic one. Now, topic two is something that's been brought up in a few other videos of what I kind of call flow engineering or adaptive RAG, which is the idea of doing tests in your RAG pipeline or in your RAG inference flow to do things like check relevance of documents, check whether or not the answer contains hallucinations. So this recent blog post from Hamil Hussein actually covers evaluation in some really nice detail. And one of the things he highlighted explicitly is actually this topic. So he talks about unit tests, and in particular, he says something really interesting here. He says, unlike typical unit tests, you want to organize these assertions in places beyond typical unit testing, such as data cleaning, and here's the key point, automatic retries during model inference. That's the key thing I want to draw your attention to. It's a really nice approach. We've talked about some other papers that do that, like corrective RAG, self-RAG, but it's also cool to see it here and kind of encapsulated in this way. The main idea is that you're using kind of unit tests in your flow to make corrections. Like if your retrieval is bad, you can correct from that. If your generation has hallucinations, you can correct from that. So I'm going to kind of draw out like a cartoon diagram of what we're going to do here. And you can kind of see it here. We're starting with a question. We talk about query analysis. We're going to take our question and we're going to decide where it needs to go. And for this particular toy example, I'm going to say either send it to a vector store, send it to web search, or just have the LLM answer it, right? So that's like kind of my fallback behavior. Then we're going to bring in that idea of kind of online flow engineering or unit testing, where I'm going to have my retrieval, either from the vector store or web search. I'm then going to ask, is this actually relevant to the question? If it isn't, I'm actually going to kick back to web search. So this is a little bit more relevant in the case if I've routed to the vector store, done retrieval, documents aren't relevant, I'll have a fallback mechanism. Then I'm going to generate. I check for hallucinations in my generation, and then I check for whether or not the generation actually answers the question. Then I return my answer. So again, we're tying together two ideas. One is query analysis, like basically taking a question, routing it to the right place, modifying it as needed, and then kind of online unit testing and iterative flow feedback. So to do this, I've actually heard a lot of people talk online about Command R, a new model release from Cohere. It has some pretty nice properties that I was kind of reading about recently. So one, it has nice support for tool use, and it does support query writing in the context of tool use. So this all rolls up in really nice capabilities for routing is kind of one. Now two, it's small. It's 35 billion parameter. It's actually open weight, so you can actually run this locally, and I've tried that. We can talk about that later. And it's also fast, served via the API. So it's kind of a small model, and it's well tuned for RAG. So I've heard a lot of people talking about using Cohere for RAG, and it has a large context, 120,000 tokens. So this is like a nice combination of properties. It supports tool use and routing. It's small and fast, so it's like quick for grading, and it's well tuned for RAG. So it's actually a really nice fit for this particular workflow where I want to do query analysis and routing, and I want to do kind of online checking and RAG. So kind of there you go. Now let's just get to the coding bit. So I have a notebook kind of like usual. I've done a few pip installs. You can see it's nothing exotic. I'm bringing LangChain Cohere. I set my Cohere API key. Now I'm just going to set this LangChain project within Langsmith. So all my traces for this go to that project. And I have enabled tracing. So I'm using Langsmith here. So we're going to walk through this flow, and let's do the first thing. Let's just build a vector store. So I'm going to build a vector store using Cohere embeddings with Chroma, open source vector DB, runs locally from 3 different web pages on blog posts that I like. So it pertains to agents, prompt engineering, and adversarial attacks. So now I have a retriever. I can run retriever invoke, and I can ask a question about, agent memory. Agent memory. And there we go. So we get documents back. So there we go. We have a retriever now. Now, here's where I'm going to bring in Cohere. I also want a router. So if you look at our flow, the first step is this routing stage, right? So what I'm going to do is, I'm just going to find 2 tools, a web search tool and a vector store tool, okay? And my preamble is just going to say you're an expert routing user questions to vector store or web search. Now here's the key. I tell it what the vector store has. So again, my vector store has agents, prompt engineering, adversarial attacks. I just repeat that here, agents, prompt eng, adversarial attacks. So it knows what's in the vector store. So use it for questions on these topics, otherwise use web search. So that's it. I use Command R here. Now I'm going to bind these tools to the model and attach the preamble, and now I have a structured LLM router. So let's give this a few tests just to kind of sandbox this a little bit. So I can here's my chain. I have a router prompt. I pass that to the structured LLM router, which I defined right here. And let's ask a few different questions, like who will the Bears draft in the NFL draft? What are the types of agent memory? And hi, how are you? So I'm going to kick that off. And you can see, it does web search, it goes to vector store, and then actually returns this false. So that's kind of interesting. This is actually just saying if it does not use either tool, so for that particular query, web search or the vector store was inappropriate, it'll just say, hey, I didn't call one of those tools. So that's interesting. We'll use that later. So that's my router tool. Now the second thing is my grader. And here's where I want to show you something really nice that is generally useful for many different problems you might encounter. So here's what I'm doing. I'm defining a data model for my grade. So basically, grade documents, it's going to this is a pedantic object. It is just basically a binary score here, field specified here. Documents are relevant to the question, yes, no. I have a preamble. Your grader assessing relevance of retrieved documents to a user question, blah, blah, blah. So, and then basically give it a binary score, yes, no. I'm using Command R, but here's the catch. I'm using this with structured outputs thing, and I'm passing my grade documents data model to that. So this is the key thing. We can test this right now as well. It's going to return an object based upon the schema I give it, which is extremely useful for all sorts of use cases. And let's actually zoom back up. So we're actually right here. So this grader stage, right, I want to constrain the output to yes, no. I don't want any preambles. I don't want anything because the logic I'm going to build in this graph is going to require a yes, no binary response from this particular edge in our graph. So that's why this grader tool is really useful. And I'm asking like a mock question, types of agent memory. I do a retriever. I do a retrieval from our vector store. I get the tuck and I test it. I invoke our grader, retrieval grader chain with the question, the doc text, and it's relevant as we would expect. So that's good. But again, let's just kind of look at that a little bit more closely. What's actually happening under the hood here? Here's the pedantic object we passed. Here's the document in question I'm providing. Basically, it's converting this object into Cohere function schema. It's binding that to the LLM. We pass in the document question. It returns an object, basically a JSON string, per our pedantic schema. That's it. And then it's just going to parse that into a pedantic object, which we get at the end of the day. So that's what's happening under the hood with this with structured output thing. But it's extremely useful. And you'll see we're going to use that a few different places because we want to ensure that in our flow here, we have 3 different grading steps. And each time we want to constrain the output to yes, no. We're going to use that structured output more than once. This is just my generation. So this is good old RAG. Let's just make sure that works. I'm using LangChain, typical RAG prompt. Again, I'm using Cohere for RAG. Pretty easy. And yeah, so the RAG piece works. That's totally fine. Nothing too crazy there. I'm going to find this LLM fallback. So this is basically if you saw our router chain, if it doesn't use a tool, I want to fall back and just fall back to the LLM. So I'm going to kind of build that as a little chain here. So, okay, this is just a fallback. I have my preamble, just you're an assistant, answer the question based upon your internal knowledge. So again, that fallback behavior is what we have here. So what we've done already is we defined our router piece. We've defined our basic retrieval, our vector store we already have here. We've defined our first logic or like grade check, and we defined our fallback. And we're just kind of roll through the parts of our graph and define each piece. So I'm going to have two other graders, and they're going to use the same thing we just talked about. Slightly different data model. I mean, same output, but actually just slightly different prompt and, you know, description. In this case, it's the answers grounded in the facts yes, no. This is my hallucination grader. And then I have an answer grader as well. And I've also run a test on each one, and you can see I'm getting binary. These objects out have a binary score. So there's a pedantic object with a binary score, and that's exactly what we want. Cool. And I have a search tool. So that's really nice. We've actually gone through and we've kind of laid out, I have like a router, I've tested it, we have a vector store, we've tested it, we've tested each of our graders here. We've also tested generation of just doing RAG. So we have a bunch of pieces built here. We have a fallback piece, we have web search. Now the question is, how do I stitch these together into this kind of flow? And for that, I like to use LangGraph. We'll talk a little bit about LangGraph versus agents a bit later, but I want to show you why this is really easy to do using LangGraph. So what's kind of nice is I've kind of laid out all my logic here. We've tested individually. And now all I'm going to do is I'm going to first lay out the parts of my graph. So what you're going to notice here is first there's a graph state. So this state represents kind of key parts of the graph, or the key kind of objects within the graph that we're going to be modifying. So this is basically a graph centered around RAG. We're going to have question, generation, and documents. That's really kind of the main things we're going to be working with in our graph. So then you're going to see something that's pretty intuitive, I think. What you're going to see is we're going to basically walk through this flow, and for each of these little circles, we're just going to find a function. And these little squares, or these, you can think about every circle as a node, and every kind of diamond here as an edge or conditional edge. So that's actually what we're going to do right now. We're going to lay out all of our nodes and edges, and each one of them are just going to be a function. And you're going to see how we do that right now. So I'm going to go down here. I define my graph state. So this is what's going to be kind of modified and propagated throughout my graph. Now all I'm going to do is I'm just going to find a function for each of those nodes. So let me kind of go side by side and show you the diagram, and then like kind of show the nodes next to it. So here's the diagram. So we have a retrieve node. So that kind of represents our vector store. We have a fallback node. That's this piece. We have a generate node. So that's basically going to do our RAG. You can see there. We have a grade documents node, kind of right here. And we have a web search node. So that's right here. Cool. Now, here's where we're actually going to find the edges. So you can see our edges are the places of the graph that are kind of making different decisions. So this route question edge, basic conditional edge, is basically going to take an input question and decide where it needs to go. And that's all we're doing down here. It kind of follows what we did up at the top, where we tested this individually. So recall, we basically just invoke that question router, returns our source. Now remember, if tool calls were not in the source, we do our fallback. So we actually showed that all the way up here. Remember this? If tool calls is not in the response, this thing will just be false. So that means we didn't call web search, and we didn't call our retriever tool. So then we're just going to fall back. Yep, right here. And this is just like a catch just in case the tool can make a decision. But most interestingly, here's where we choose a data source, basically. So this is the output of our tool call. We're just going to fish out the name of the tool. So that's data source. And then here we go. If the data source is web search, I'm returning web search as basically the next node to go to. Otherwise, if it's vector store, return vector store as the next node to go to. So what's this web search thing? Well, remember, we right up here define this node web search. That's it. We're just going to go to that node. What's this vector store? You'll see below how we can kind of tie these strings that we returned from the conditional edge to the node we want to go to. That's really it. Same kind of thing here, decide to generate. That's going to roll in these two conditional edges into one. And basically it's going to do if there's no documents. So basically if we filtered out all of our documents from this first test here, then what we're going to do is we've decided all documents are not relevant to the question, and we're going to kick back to web search exactly as we show here. So that's this piece. Otherwise, we're going to go to generate. So that's this piece. So again, in these conditional edges, you're basically implementing the logic that you see in our diagram right here. That's all that's going on. And again, this is just implementing the final two checks for hallucinations and answer relevance. Yep, so here's our hallucination grader. We then extract the grade. If basically there are hallucinations, in this case, the grade actually, yes, means that the answer is grounded. So we say the answer is actually grounded, and then we go to the next step. We go to the next test. That's all this is doing. It's just basically wrapping this logic that we're implementing here in our graph. So that's all that's going on, and let's go ahead and define all those things. So nice, we have all that. Now we can actually go down a little bit, and we can pull... this is actually where we stitch together everything. So all that's happening here is, you see we defined all these functions up here. We just add them as nodes in our graph here, and then we build our graph here basically by basically laying out the flow or the connectivity between our nodes and edges. So, you can look at this notebook to kind of study in a bit of detail what's going on, but frankly, what I like to do here typically, just draw out a graph, kind of like we did up here, and then implement the logical flow here in your graph as nodes and edges, just like we're doing here. That's all that's happening. So again, we have like our entry point is the router. This is like the output this is basically directing like, here's what the router is outputting, and here's the next node to go to. So that's it. And then for each node, we're kind of applying, like, we're saying like, what's the flow? So web search goes to generate after, and retrieve goes to grade documents. Grade documents kind of is a conditional edge. Depending on the results, we either do web search or generate. And then our second one, we go from generate to basically this grade generation versus documents in question. Based on the output of that, we either have hallucinations, we regenerate, we found that the answer is not useful, we kick back to web search, or we end. Finally, we have that LLM fallback, and that's also, if we go to the fallback, we end. So what you're seeing here is actually the logic flow we're laying out in this graph matches the diagram that we laid out up top. I'm just going to copy these over, and I'll actually go then back to the diagram and kind of underscore that a little bit more. So here is the flow we've laid out. Again, here is our diagram, and you can kind of look at them side by side and see how they basically match up. So here's kind of our flow diagram going from basically query analysis. That's this thing, this route question. And you can see web search, vector store, LLM fallback, web search, vector store. So those are like the three options that can come out of this for conditional edge. And then here's where we connect. So if we go to web search, then basically we next go to generate. So that's kind of this whole flow. Now if we go to retrieve, then we're going to grade. So that's it. And, it follows kind of as you can see here. That's really it. So it's just nice to draw these diagrams out first. And then it's pretty quick to implement each node and each edge just as a function, and then stitch them together in a graph just like I show here. And of course, we'll make sure this code's public so you can use it as a reference. So there we go. Now let's try a few different test questions. So like, what player of the Bears expected to draft in the NFL draft, right? Let's have a look at that. And this should print everything it's doing as we go. So, okay, this is important. Route question, it decides to route to web search. That's good. It doesn't go to our vector store. This is a current event, not related to our vector store at all. It goes to web search, and then it goes to generate. So that's what we'd expect. So basically, web search goes through to generate, and we check hallucinations. Generation is grounded in the documents. We check generation versus question. The generation addresses the question. The Chicago Bears expected to draft Caleb Williams. That's right. That's the consensus. So cool. That works. Now let's ask a question related to our vector store. What are the types of agent memory? We'll kick this off. So we're routing. Okay, we're routing to RAG. Now look how fast this is. That's really fast. So we basically whip through that document grading, determine they're all relevant. We go to the decision to generate. We check hallucinations. We check answer versus question. And there are several types of memory stored in the human brain. Memory can also be stored in generative agents. You have LLM-powered agents, memory stream retrieval model, and reflection mechanisms. So it's representing what's captured in the blog post pretty reasonably. Now, let me show you something else that's kind of nice. I can go to Langsmith, and I can go to my projects. We create this new project, Cohere Adaptive RAG, at the start, and everything is actually logged there, everything we just did. So I can open this up, and I can actually just kind of look through all the stages of my LangGraph to here's my retrieval stage, here's my grade document stage, and we can kind of audit the grading itself. We kind of looked at this one by one previously, but it's actually pretty nice. We can actually audit every single individual document grade to see what's happening. We can basically go through to, this is going to be one of the other graders here. Yep, so this is actually going to be the hallucination grading right here. And then this is going to be the answer grading right here. So that's really it. You can kind of walk through the entire graph. You can kind of study what's going on, which is actually very useful. So it looks like this worked pretty well. And finally, let's just ask a question that should go to that fallback path down at the bottom, like not related at all to our vector store current events. And yeah, hello, I'm doing well. So it's pretty neat. We've seen in maybe 15 minutes, we've from scratch built basically a semi-sophisticated RAG system that has agentic properties. We've done it in LangGraph. We've done with Cohere Command R. You can see it's pretty darn fast. In fact, we can go to Langsmith and look at, so this whole thing took 7 seconds. That is not bad. Let's look at the most recent one. So this takes 1 second. So the fallback mechanism to the LLM is like 1 second. Let's just look here. So 6 seconds for the initial LangGraph. So this is not bad at all. It's quite fast. It does quite a few different checks. We do routing, and then we have kind of a bunch of nice fallback behavior and inline checking for both relevance, hallucinations, and answer kind of groundedness or answer usefulness. So, this is pretty nice. I definitely encourage you to play with a notebook. Command R is a really nice option for this due to the fact that it's tool use, routing, small and quite fast, and it's really good for RAG. So it's a very nice kind of a very nice option for workflows like this. And I think you're going to see more and more of this kind of like adaptive or self-reflective RAG, just because this is something that a lot of systems can benefit from. Like a lot of production RAG systems kind of don't necessarily have fallbacks, depending on, for example, like, if the documents retrieved are not relevant, if the answer contains hallucinations, and so forth. So this opportunity to apply inline checking along with RAG is like a really nice theme. I think we're going to see more and more of, especially as model inference gets faster and faster, and these checks get cheaper and cheaper to do kind of in the inference loop. Now, as a final thing, I do want to bring up a point about, we've shown this LangGraph stuff. What about agents? How do you think about agents versus LangGraph, right? And I think the way I like to frame this is that LangGraph is really good for flows that you have kind of very clearly defined, that don't have like kind of open-endedness, but like in this case, we know the steps we want to take every time. We want to do basic query analysis routing, and then we want to do 3 grading steps, and that's it. LangGraph is really good for building very reliable flows. It's kind of like putting an agent on guardrails, and it's really nice. It's less flexible, but highly reliable. And so you can actually use smaller, faster models with LangGraph. So that's the thing I like about, we saw here Command R, 35 billion parameter model, works really well with LangGraph. It's quite quick. We were able to implement a pretty sophisticated RAG flow really quickly, 15 minutes, Inference time is on the order of like less than, around 5 to 6 seconds. So pretty good, right? Now, what about agents, right? So I think agents come into play when you want more flexible workflows. You don't want to necessarily follow a defined pattern a priori. You want an agent to be able to kind of reason and make open-ended decisions, which is interesting for certain like long horizon planning problems. Agents are really interesting. The catch is that reliability is a bit worse with agents, and so that's a big question a lot of people bring up. And that's kind of where larger LLMs kind of come into play with, there's been a lot of questions about using small LLMs, even open source models with agents, and reliability has kind of continuously been an issue. Whereas I've been able to run these types of land graphs with like Mistral, or Command R actually is open weights. You can run it locally. I've been able to run them very reproducibly with open source models on my laptop. So I think there's a trade-off. And there's a new Cohere model coming out, I believe Command R Plus, which is a larger model, so it's probably more suitable for kind of more open-ended agentic use cases. And there's actually a new integration with LangChain that support Cohere agents, which is quite nice. So I think it's worth experimenting for certain problems and workflows. You may need more open-ended reasoning, in which case use an agent with a larger model. Otherwise, you can use like LangGraph for a more reliable potentially, but constrained flow, and it can also use smaller models, faster LLMs. So those are some of the trade-offs to keep in mind. But anyway, I encourage you, play with a notebook, explore for yourself. I think Command R is a really nice model. I've also been experimenting with running it locally with Ollama. Currently, the quantized model is like 2-bit quantized is like 13 billion. 13 gigs. It's a little bit too large to run quickly locally for me. Inference for things like RAG were on the order of 30 seconds. So again, it's not great for a live demo, but it does work. It is available on Ollama, so I encourage you to play with that. I have a Mac M2 32 gig. So if you have a larger machine, then it absolutely could be worth working with locally. So encourage you to play with that. Anyway, hopefully this was useful and interesting. I think this is a cool paper, cool flow. Cohere Command R is a nice option for these types of like routing. It's quick, good with LangGraph, good for RAG, good for tool use. So have a look and reply anything, any feedback in the comments. Thanks.
Hi, this is Lance from LangChain. This is a talk I gave at 2 recent meetups in San Francisco called "Is RAG Really Dead?" And I figured since a lot of people actually weren't able to make those meetups, I just record this and put this on YouTube and see if this is of interest to folks. So we all kind of recognize that context windows are getting larger for LLMs. So on the x-axis, you can see the tokens used in pre-training. That's of course getting larger as well. Proprietary models are somewhere over the 2 trillion token regime. We don't quite know where they sit. And we've all the way down to smaller models like 5.2 trained on far fewer tokens. But what's really notable is on the y-axis, you can see about a year ago, state-of-the-art models were on the order of 4,000 to 8,000 tokens, and that's dozens of pages. We saw Claude 2 come out with a 200,000 token model earlier. I think it was last year. GPT-4 with 128,000 tokens. Now that's hundreds of pages. And now we're seeing Claude 3 and Gemini come out with million token models. So this is hundreds to thousands of pages. So because of this phenomenon, people have been kind of wondering, is RAG dead? If you can stuff many thousands of pages into the context window of an LLM, why do you need a retrieval system? It's a good question. It sparked a lot of interesting debate on Twitter. And it's maybe first just kind of grounding on what is RAG. So RAG is really the process of reasoning and retrieval over chunks of information that have been retrieved. It's starting with documents that are indexed. They're retrievable through some mechanism, typically some kind of semantic similarity search or keyword search, other mechanisms. Retrieved docs are then passed to an LLM, and the LLM reasons about them to ground response to the question in the retrieved document. So that's kind of the overall flow. But the important point to make is that typically it's multiple documents and involves some form of reasoning. So one of the questions I asked recently is, if long context LLMs can replace RAG, it should be able to perform, multi-fact retrieval and reasoning from its own context really effectively. So I teamed up with Greg Cameron to kind of pressure test this. And he had done some really nice needle in the haystack analyses already, focused on kind of single facts called needles placed in a haystack of Paul Graham essays. So I kind of extended that to kind of mirror the RAG use case or kind of the RAG context, where I took multiple facts. So I call it multi-needle. I built on a funny needle in the haystack challenge published by Anthropic, where they basically placed pizza ingredients in the context and asked the LM to retrieve this combination of pizza ingredients. I kind of riffed on that, and I basically split the pizza ingredients up into 3 different needles and placed those 3 ingredients in different places in the context, and then asked the LM to recover those 3 ingredients from the context. So again, the setup is, the question is whether the secret ingredients need to build a perfect pizza. The needles are the ingredients: figs, prosciutto, goat cheese. I place them in the context at some specified intervals. So the way this test works is you can basically set the percent of context you want to place the first needle, and the remaining 2 are placed at roughly equal intervals in the remaining context after the first. So that's kind of the way the test is set up now. It's all open source, by the way. The link is below. So the needles are placed. You ask a question, you prompt LLM with kind of with this context in the question, and then produces the answer. And now the framework will grade the response. Both, one, are all the specified ingredients present in the answer, and 2, if not, which ones are missing. So I ran a bunch of analysis on this with GPT-4 and came up with some fun results. So you can see on the left here, what this is looking at is different numbers of needles placed in a 120,000 token context window for GPT-4. And I'm asking GPT-4 to retrieve either 1, 3, or 10 needles. Now, I'm also asking it to do reasoning on those needles. That's what you can see in those red bars. So green is just retrieve the ingredients, red is reasoning, and the reasoning challenge here is just return the first letter of each ingredient. So we find is basically 2 things. The performance, or the percentage of needles retrieved, drops with respect to the number of needles. That's kind of intuitive. You place more facts, performance gets worse. But also it gets worse if you ask it to reason. So if you say, just return the needles, it does a little bit better than if you say return the needles and tell me the first letter. So you overlay reasoning. So this is the first observation. More facts is harder, and reasoning is harder than just retrieval. Now, the second question we ask is, where are these needles actually present in the context that we're missing, right? So we know, for example, retrieval of 10 needles is around 60%. So where are the missing needles in the context? So on the right, you can see results telling us actually which specific needles the model fails to retrieve. So what we can see is, as you go from 1,000 tokens up to 120,000 tokens on the X here, and you look at needle 1 placed at the start of the document to needle 10 placed at the end, at 1,000 token context length, you can retrieve them all. So again, kind of match what we see over here. Over here, everything I'm looking at is 120,000 tokens. So that's really not the point. The point is actually smaller context, better retrieval. So that's kind of point 1. As I increase the context window, I actually see that there is increased failure to retrieve needles, which you can see in red here, towards the start of the document. And so this is an interesting result. And it actually matches what Greg saw with single needle case as well. So the way to think about it is, it appears that if you, for example, read a book and I ask you a question about the first chapter, you might have forgotten it. Same kind of phenomenon appears to happen here with retrieval, where needles towards the start of the context are kind of forgotten or are not well retrieved relative to those at the end. So this is an effect we see with GPT-4. It's been reproduced quite a bit. So I ran 9 different trials here. Greg's also seen this repeatedly with single needle. So it seems like a pretty consistent result. And there's an interesting point. I put this on Twitter, and a number of folks, replied, and someone sent me this paper, which is pretty interesting. And it mentions recency bias as one possible reason. So the most informative tokens for predicting the next token, are present close to or recent to kind of where you're doing your generation. And so there's a bias to attend to recent tokens, which is obviously not great for the retrieval problem, as we saw here. So again, the results show us that reasoning is a bit harder than retrieval, more needles is more difficult, and needles towards the start of your context are harder to retrieve than towards the end. Those are the three main observations from this. And it may be indeed due to this recency bias. So overall, what this kind of tells you is be wary of just context stuffing in long context LLMs. There are no retrieval guarantees. And also there's some recent results that came out actually just today suggesting that single needle may be misleadingly easy. There's no reasoning. It's retrieving a single needle. And also these guys, I showed this tweet here, show that in a lot of these needle in the haystack challenges, including mine, the facts that we look for are very different than the background kind of haystack of Paul Graham essays. And so that may be kind of an interesting artifact. They note that indeed, if the needle is more subtle, retrieval is worse. So I think basically when you see these really strong performing needle in the haystack analyses put up by model providers, you should be skeptical. You shouldn't necessarily assume that you're going to get high quality retrieval from these long context LLMs for numerous reasons. You need to think about retrieval of multiple facts. You need to think about reasoning on top of retrieval. You need to think about the subtlety of the retrieval relative to the background context, because for many of these needle in the haystack challenges, it's a single needle, no reasoning, and the needle itself is very different from the background. So anyway, those may all make the challenge a bit easier than a real world scenario of fact retrieval. So I just want to kind of lay out those cautionary notes. But, I think it is fair to say this will certainly get better. And I think it's also fair to say that RAG will change. And this is just like really not a great joke, but Frank Zappa, musician, made the point, jazz isn't dead, it just smells funny. I think same for RAG. RAG is not dead, but it will change. I think that's kind of the key point here. So just as a follow-up on that, RAG today is focused on precise retrieval of relevant doc chunks. So it's very focused on typically taking documents, chunking them in some particular way, often using very idiosyncratic chunking methods. Things like chunk size are kind of picked almost arbitrarily, embedding them, storing them in an index, taking a question, embedding it, doing KNN similarity search to retrieve relevant chunks. You're often setting a K parameter, which is the number of chunks you retrieve. You often will do some kind of filtering or post-processing on the retrieved chunks, and then ground your answer in those retrieved chunks. So it's very focused on precise retrieval of just the right chunks. Now, in a world where you have very long context models, I think there's a fair question to ask is this really kind of the most reasonable approach? So kind of on the left here, you can kind of see this notion closer to today of I need the exact relevant chunk. You can risk over engineering. You can have higher complexity, sensitivity to these odd parameters like chunk size, K, and you can indeed suffer lower recall because you're really only picking very precise chunks. You're beholden to very particular embedding models. So, I think going forward, as long context models get better and better, there are definitely you should certainly question the current kind of very precise chunking RAG paradigm. But on the flip side, I think just throwing all your docs into context probably will also not be the preferred approach. You'll suffer higher latency, higher token usage. I should note that today, 100,000 token GPT-4 is like $1 per generation. I spent a lot of money on LangChain's account on that multi-needle analysis. I don't want to tell Harrison how much I spent. So it's not good, right? You can't audit retrieval. And security and authentication are issues if, for example, you need different users, different access to certain kind of retrieved documents or chunks. In the context stuffing case, you kind of can't manage security as easily. So there's probably some Pareto optimal regime kind of here in the middle. And, I put this out on Twitter. I think there's some reasonable points raised. I think, this inclusion at the document level is probably pretty sane. Documents are self-contained chunks of context. What about document-centric RAG? So no chunking, but just operate on the context of full documents. So, if you think forward to the RAG paradigm that's document-centric, you still have the problem of taking an input question, routing it to the right document. This doesn't change. So I think a lot of methods that we think about for kind of query analysis, taking an input question, rewriting it in a certain way to optimize retrieval, Things like routing, taking a question, routing it to the right database, be it a relational database, graph database, vector store, and query construction methods. So for example, text to SQL, text to Cipher for graphs, or text to even like metadata filters for vector stores. Those are all still relevant in the world that you have long context LLMs. You're probably not going to dump your entire SQL DB and feed that to the LLM. You're still going to have SQL queries. You're still going to have graph queries. You may be more permissive with what you extract, but it still is very reasonable to store the majority of your structured data in these forms. Likewise, with unstructured data like documents, like we said before, it still probably makes sense to store documents independently, but just simply aim to retrieve full documents rather than worrying about these idiosyncratic parameters like chunk size. And along those lines, there's a lot of methods out there. We've done a few of these that are kind of well optimized for document retrieval. So one I want to flag is what we call multi-representation indexing. And there's actually a really nice paper on this called dense X retriever or proposition indexing. But the main point is simply this. What you do is you take your raw document, you produce a representation, like a summary of that document, you index that summary, right? And then at retrieval time, you ask your question, you embed your question, and you simply use a high-level summary to just retrieve the right document. You pass the full document to the LLM for kind of final generation. So it's kind of a nice trick where you don't have to worry about embedding full documents in this particular case. You can use kind of very nice descriptive summarization prompts to build descriptive summaries. And the problem you're solving here is just get me the right document. It's an easier problem than get me the right chunk. So this is kind of a nice approach. There's also different variants of it, which I share below. One is called parent document retriever, where you could use, in principle, if you wanted, smaller chunks, but then just return full documents. But anyway, the point is preserving full documents for generation, but using representations like summaries or chunks for retrieval. So that's kind of like approach one that I think is really interesting. Approach two is this idea of RAPTOR. It's a cool paper, came out of Stanford somewhat recently, and this solves the problem of what if for certain questions I need to integrate information across many documents. So what this approach does is it takes documents and it embeds them and clusters them, and then it summarizes each cluster. And it does this recursively until you end up with only one very high-level summary for the entire corpus of documents. And what they do is they take this kind of this abstraction hierarchy, so to speak, of different document summarizations, and they just index all of it. And they use this in retrieval. And so basically, if you have a question that draws in information across numerous documents, you probably have a summary present and indexed that kind of has that answer captured. And so it's a nice trick to consolidate information across documents. Their paper actually reports, these documents in their case, or the leafs, are actually document chunks or slices. But I actually showed, I have a video on it in a notebook, that this works across full documents as well. And that's a nice segue into, to do this, you do need to think about long context embedding models because you're embedding full documents. And that's a really interesting thing to track. The HyDE research put out a really nice blog post on this using with the Monarch mixer. So it's kind of a new architecture that attends to longer context. They have a 32,000 token embedding model that's available on Together AI. Absolutely worth experimenting with. I think this is a really interesting trend. So long context embeddings kind of play really well with this kind of idea, where you take full documents, embed them using, for example, long context embedding models, and you can kind of build these document summarization trees really effectively. So I think this is another nice trick for working with full documents in the long context kind of LLM regime. One other thing I'll note, I think there's also going to move away from kind of single shot RAG. Well, today's RAG, we typically, we chunk documents, and embed them, store them in an index, do retrieval, and then do generation. But there's no reason why you shouldn't kind of do reasoning on top of the generation or reasoning on top of the retrieval and feed back if there are errors. So there's a really nice paper called Self-RAG that kind of reports this. We implemented this using LangGraph, works really well. And the idea is simply to grade the relevance of your documents relative to your question first. If they're not relevant, you rewrite the question. You can do many things. In this case, we do question rewriting and try again. We also grade for hallucinations. We grade for answer relevance. But anyway, it kind of moves RAG from a kind of single shot paradigm to a kind of a cyclic flow in which you actually do various gradings downstream. And this is all relevant in the long context LLM regime as well. In fact, you absolutely should take advantage of, for example, increasingly fast and performant LLMs to do these grading. Frameworks like LangGraph allow you to build these flows, which allows you to kind of have a more performant kind of self-reflective RAG pipeline. Now, I did get a lot of questions about latency here, and I completely agree. There's a trade-off between kind of performance, accuracy, and latency that's present here. I think the real answer is you can opt to use very fast, for example, models like Grok we're seeing, GPT-3.5 turbos very fast. These are fairly easy grading challenges, so you can use very, very fast LLMs to do the grading. And for example, you can also restrict this to only do one turn of a kind of cyclic iteration, so you can kind of restrict the latency in that way as well. So anyway, I think it's a really cool approach, still relevant in the world as we move towards longer context. So it's kind of like building reasoning on top of RAG in the generation and retrieval stages. And a related point, one of the challenges with RAG is that your index, for example, you may have a question that asks something that's outside the scope of your index, and this is kind of always a problem. So a really cool paper called CRAG or corrective RAG came out, a couple months ago that basically does grading, just like we talked about before. And then if the documents are not relevant, you kick off and do a web search and basically return the search results to the LM for final generation. So it's a nice fallback in cases where the question's out of the domain of your retriever. So, again, nice trick, overlaying reasoning on top of RAG. I think this trend, continues because, it makes RAG systems, more performant and less brittle to questions that are out of domain. So, that's another kind of nice idea. This particular approach also we showed works really well with open source models. So I ran this with Mistral 7B. It can run locally on my laptop using Llama. So again, really nice approach. I encourage you to look into this. And this is all kind of independent of the LLM kind of context length. These are reasoning you can add on top of the retrieval stage that can kind of improve overall performance. And so the overall picture kind of looks like this, where, I think that the problem of routing your question to the right database and or to the right document kind of remains in place. Query analysis is still quite relevant. Routing is still relevant. Query construction is still relevant. In the long context regime, I think there is less of an emphasis on document chunking. Working with full documents is probably kind of more Pareto optimal, so to speak. There's some clever tricks for indexing of documents, like the multi-representation indexing we talked about. The hierarchical indexing using RAPTOR that we talked about as well are two interesting ideas for document-centric indexing. And then kind of reasoning and generation post-retrieval on retrieval itself to grade, on the generations themselves, checking for hallucinations. Those are all kind of interesting and relevant parts of a RAG system that I think we'll see more and more of as we move more away from like a more naive prompt response paradigm, more to like a flow paradigm. We're seeing that actually already in code generation. It's probably going to carry over to RAG as well, where we kind of build RAG systems that have kind of a cyclic flow to them, operate on documents, use long context LLMs, and still use kind of routing and query analysis. So reasoning pre-retrieval, reasoning post-retrieval. So anyway, that was kind of my talk. And yeah, feel free to leave any comments on the video and I'll try to answer any questions. But yeah, that's probably about it. Thank you.